Welcome back, everyone. This is Lecture 10a, Noise Mitigation via Software Solutions. I'm Jonathan Baker. In previous videos, we've discussed several high-level ideas for quantum compilation: mapping, routing, scheduling. The objectives in these cases were often classical: ensure program qubits are mapped close together to minimize communication overhead, also implying a good routing strategy to do this. And we want to schedule the programs in a way which makes sure they execute quickly. Similarly, in classical compilation, optimization a prominent goal of optimization is to ensure that what the program wants to write is executed quickly. Error is not nearly as dominant there as it is for current quantum devices. One of the biggest challenges facing quantum computing community is noise mitigation. Without strategies to reduce or get around physical noise, gates being imperfectly executed, quantum states decohering, for example, any execution of the quantum program is almost doomed to fail on these devices. And by failure, we mean something a little more than didn't get the right answer. Since when we execute with imperfect operations and we execute the program numerous times, we obtain a distribution of answers at the end of the program. And so failure here means something like the correct answer isn't reliably discernible from all the other answers obtained. And we might also have multiple right answers. Current NISQ computers, the current age of quantum devices, lack the ability to isolate and control a large number of quantum bits with high precision. Scaling up a quantum computer requires us to increase not only the number of qubits available, but also the quality of those qubits as well. Just adding extra qubits to accommodate larger programs is not going to be sufficient if the error is too great to get a meaningful answer from the computer. In this lecture, we want to talk about how to adapt some of the strategies that we wrote for. So for mapping, scheduling, and routing, to account for error. So now this is now with error. In previous lectures, we argued for the need for short programs and programs with smaller number of operations with error in mind, but only implicitly. We said that if we had short programs, then we wouldn't incur a lot of decoherence, and if we had programs that used a small number of gates, then we wouldn't have as much gate error. But now we're going to explicitly try to maximize an objective which depends directly on error, so something like reliability for our program. Okay, so in this lecture, we're going to focus on compilation strategies which mitigate this error by accounting for device variation. Current devices aren't just noisy, but they're also highly variable as well. So for example, we might have a superconducting device, which is often our example, which is this device. And the gates executed on different pairs of qubits, so let's just label some. So we might expect that the error of a gate between A and B might be worse, greater than the error to execute the same type of gate on B and C, for example. So we would want to avoid maybe using lots of instances of gates on A and B, and instead prefer to use lots of gates using B and C because there's less error on here. But there's also other things that vary, and it's not just across the device. So we might have different measurement error between on qubit A. So if I measure qubit A, then there's a chance that maybe I get the wrong answer just because it's measured improperly. Or similarly for B, and we might want to choose how we map depending on these measurement errors. But we also have variation in time. So if at t0 this statement is true, then maybe if we wait 2 days or something, that it's no longer true. So at T1, we write the same device, but now the edge between A and B might be worse than the edge between B and C. And so we would need to adapt our compilation strategy to account for this variation. So there's not just a lack of uniformity in the device itself, because it's hard to manufacture the same consistent qubits, but also across time. And so we need to make sure that our compilation isn't just one fixed strategy based on either maybe the connectivity or something. And the output that we produce with the compilation at T0 might become stale as time passes. How fast it changes is still open. You'd have to figure out based on the device. And if you knew like when a good time to redo this was, you could sort of choose your strategy based on the time. Okay, so what can we do? We can adjust our strategies from before, our mapping, routing, and scheduling passes, to directly account for this variation, both in time and across the device. Okay, so let's look at some straightforward heuristics to solve this problem. In previous videos, we often accounted for the hardware connectivity graph, that same thing we just solved before, so hardware. Our small example again. Where qubits in these devices have limited connectivity. So for example, qubit A here has only 2 neighbors that it can interact with. And this graph was really important for lots of different reasons, mostly indicating how far qubits might need to move in order to interact with other qubits. So for example, if we just finish labeling these, in order to interact with qubits A and F, we know that we'd have to move through other qubits in order to interact program qubits that are mapped far apart. However, this graph can also be extended to account for more hardware information. So before, we indicated that the length of the path between pairs of qubits indicated how many swaps we'd need to communicate. So we had maybe between A and F, we know we'd have to swap between A to B, this is just one example, and then B to E, and then we would execute our desired gate between E and F. But now we want, and so the length of this path between A and F indicated how many swaps we needed. There was 2 links between them. But now we want the lengths of the paths to indicate which is the most reliable, or the one with the lowest gate error, or possibly even the shortest duration, because we might expect that the gates executed on different edges take different amounts of time to execute. Maybe this one takes 150 nanoseconds, and this one over here only takes 70 nanoseconds, for example. Similarly, we might also want to label the nodes themselves, not just the edges, to account for single qubit gate durations, errors, and perhaps most importantly, readout errors, which are often on the order of the error of 2 qubit gates. The objective that the heuristic that we use may take advantage of some or all of this information when deciding how to map, route, and schedule. Okay, I want to take a brief aside to talk about coherence error in optimization objectives. One approach is simply to require that all gates on a qubit execute within the coherence window of the qubit. So for example, if I know for qubit A has a specific T1 time, which is this coherence time for qubit A, then when I look at the program graph for A, I want to make sure that this whole window is at most duration T1. So if any gates are scheduled on here, maybe here, 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 and here, that they all need to have finished before this T1 window. And then we could say that if it's not possible to do that, say we needed to execute a gate over here, which is outside of this coherence window. Say we initialized it here. This is the first gate here. This is the first gate. So we can think about active volume in this case too. But we had to, for some reason, execute this gate outside of that coherence window. Then we could just say, this program can't be run. I can't schedule all of the gates I want to for all my qubits in an appropriate amount of time. So this strategy can be considered too restrictive in one sense. So on one hand, it says that programs cannot be executed if they can't all be scheduled at the right time. But it can also be too lenient. There is a probability of error even if all the gates fit within the window. We might want to reward programs which minimize total active volume more. So we might want to say, okay, well, your last gate was here at this like T star time, which is less than T1. And we don't want to say, okay, that's good. That is beneficial, and we should prefer things that do this for our qubits. One way to approximate the coherence time error is to take x of total active volume, to how long it's being used for, and then divide it by its T1 time. This is just one way to approximate this. And so you can see that if the total active volume is much smaller than the T1 time, then this value will be close to 0. Many current machines make accessible this information about coherence times and gate durations, and we can use that to make approximations about this error. Okay, so let's talk about a simple heuristic for mapping and scheduling that uses all this extra information we just talked about. For convenience, we're going to pre-compute what are considered the shortest paths between all pairs of nodes in the hardware graph. So we can keep a data structure that keeps track of this, and this is efficient to find all these things. Error rates, however, are not additive. So, for example, if I know that I have error rate 1 for edge UV, this is the error rate to execute on that edge, and I have maybe error rate 2 to execute between x and y, a different pair of qubits, then the error rate to execute on one edge on UV and one edge on XY is not equal to the sum of this. This is not true. Instead, it would be error 1 times error 2. We want to say that there's a probability of doing, since these are probabilities of it successfully executing. So this is slightly harder for our pathfinding algorithm that wants to find all pairs' shortest path between all the pairs of nodes, because those algorithms typically rely on them being additive. But we could notice that the log of E1 times E2 is equal to the log of E1 plus the log of E2. So this is now additive. But we also note that all these E1s are less than 1, or less than 0. These are all negative values. Or the E's are less than 1, and so the logs of them are negative values. So we have to do some adjustment as well there to make use of some out-of-the-box algorithms. Okay, so also one other note is that gate errors, so when I report E1 here for the edge UV, it might also include coherent error already in how it's reported. And so if we also include some other error term that accounts like from here above, then we might be double counting, and so we need to be aware of what that reported value indicates. Okay, so then how does our algorithm work? It's really simple. We don't need too much space. We first begin by constructing our program dependency graph as before. So as a quick reminder, for every program qubit, we have a node and edges between program qubits that interact, and they're weighted by the number of times they interact. So this is A, B, and C. Then the weight between B and C would say that qubits B and C in the program interact 7 times. Okay. So the first step is to just find the highest weighted edge of this graph. So say we have 5, 7, and 2. Then we would just select B and C in this program graph. So BC is the one we're starring. And we're going to just map that edge to the edge in the hardware with the best reliability. So if I look at our hardware graph from the top left, if we have all of these error values indicated along the edges, we can just select the best one. The reason being that if this program qubits interact really frequently, then doing lots of operations on them will be, we want to make sure that those operations use a good edge so they don't incur too much extra cost. Clearly, there might be many choices that we could adapt here instead of just choosing the best edge in the device. We might also try to place some larger subgraphs, so say we wanted to just place this whole 3-qubit thing on the device. Or we might want to map the edge not just to the highest reliability edge, but maybe look at the top k edges and choose the one that has the best relative connectivity or is closest to the graph center. Okay, so then the next step would be to then look at all of the other, let's just draw our example down here and map our qubits. Let's call these A prime, B prime, and C prime so we don't have conflicting labels. And say, for example, this middle edge between B and E is actually the best. So then we would make an assignment from B to B prime. So these are mapped to each other. And E to C prime. So that C prime is mapped into E and B prime is mapped into B. So then for every subsequent edge that's connected to this edge, so now we're looking at the edges A prime, C prime, and A prime, B prime. And we want to look at, we want to compute some score about where those edges should go. So for example, we could consider placing A by looking at all of the hardware graphs. We could look at all these things and compute the reliability of a path between the candidate, so say this is our candidate, to all of the other qubits that it's mapped to, it's connected to in its program dependency. So here, A prime is connected to both C prime and B prime, so we would look at paths to both of these two things in their mapping. and we compute a score based on that, which might be the product of all of the gates along the edge, etc. Okay, so now this strategy implicitly routes for us in a swap there, swap back fashion, because we're choosing the highest reliability path between the hardware qubits. And recall from before, this can cause congestion, so we might want to do some adaptation to that. And then essentially we just repeat this process until we've found a mapping, until everything has been mapped. And this gives us both our mapping and our routing if we want it, and then we just need to schedule. Okay, in a previous lecture, I promised something about optimality for something beyond just the scheduling problem. And we noted that solving optimally the mappings, routings, and scheduling is ultimately hard. We could end up taking an exponential time to find the best solutions to these problems, even without all of this error information. We also introduced some optimization frameworks in the form of LP and ILP, linear programming and integer linear programming. And I want to revisit these strategies and frame some of these noise-aware problems in that language. So let's just write these constraints and think about logically what they mean. And then it would be something that we could directly feed into something like an ILP or SMT solver. And then finally, we'll talk about objectives at the end. So for this, we're going to assume n rows and m columns of a grid architecture. So let's also assume that a swap there, swap back strategy is being used. Adding in a time dimension to sort of account for where each qubit is on the device at every time will explode the number of variables, and so we're going to do a simplified version of this. So with this assumption, we can pre-compute the duration of every operation as the duration of a gate on that edge that it's executing on, wherever we've mapped it to, plus whatever the duration of the whole swap path to get there was, plus the amount of time to come back. So if I have maybe a location here and location here, it's not just the time it takes to execute on this thing where it ends up, but how long it took to get there. So this whole path there, plus this time on this edge, and then we had to swap back. And so we're going to take we can pre-compute all of that. Okay, so let's talk about constraints. So for every Q in my hardware, we want to say that 0 is less than the x coordinate of that qubit is less than m, and then also that the y coordinate is less than n. So this specifies that it has to be somewhere on the hardware. Second, we want to say that no two qubits can be mapped to the same location. So if we have, for every pair of qubits q1, q2, that q1.x is not equal to q2.x, or q1.y is not equal to q2.y. So one of these two coordinates must be different for them to be in different positions in the hardware. For a more exotic graph, instead of just this grid model that we're using here, we could just assign indices to each node and assert that two nodes do not have the same index. We also could pre-compute paths between these nodes as well. Okay, so note that each of these qi.x and qi.y things are integers. So this is already going to be a hard problem to solve for some meaningful objective, rather than just saying, is there a mapping? Okay, so let's add in some scheduling constraints. We've already seen these before. So if we have gates G1 and G2, and then if we know that in our dependency graph that G2 depends on G1, then we can say that, and if we write that as, let's see, G2 depends on G1, then the time that G2 starts, G2.t, must be bigger than when G1 started, plus how long it took this to execute, so duration. Okay, so this G1 duration includes the swapping and communication, but it's variable. This is not known a priori because we don't know where the qubits that gate 1 executes on are going to be mapped in the hardware. So we don't know which path it's choosing until the solver begins to go and selects some locations. So we'll have to assign this. So we have to write a constraint that will assign what duration is. Okay, so let's write this constraint. So if G, for every G that and we'll just assume that this is on qubits A and B, program qubits A and B, then if the hardware location of A, so H of A, is equal to some hardware location H1, and H of B is some other location H2, then this will imply that the duration, g dot duration, is equal to some pre-computed value, big delta of h1, h2. So we can pre-compute this, because we know for hardware locations what the duration of a gate will take, because that's fixed. But we don't know where A and B are mapped to. We don't know that it's h1 or h2 beforehand, and that's assigned during solving. Okay, so then we want to write a constraint that ensures that all the gates occur within the coherence time. So, for example, we could say same thing for all G, and then we're going to assume it's on qubits A and B. For single qubit gates, you can adapt this similarly. Then if h of A is equal to h1 and h of B is equal to h2, then this is going to imply that the duration, the start time of t plus its or of the gate plus its duration, remember this is being assigned above, must be less than. So we want to assume that we want to force that it finishes before the coherence times. So this is the coherence time of h1. This is the min. It must occur before both of these, and the coherence time of h2. So this just says, for any gate, we want to make sure that all the gate, that when it occurs, it's before either one of the hardware qubits is decohered. Okay. So let's go to the next slide here. In this example, we're fixing the routes that must be taken, so we don't need to include routing constraints, though it is possible. There are many possible routes one could take, though, in a grid or any other graph. And so a good strategy would be to fix certain types of paths that you can choose and just have the solver choose between a smaller set of things rather than all possible paths on the device, and also not adding in this extra time constraint. Okay, so the final things we need to include are some reliability constraints. Because we don't know where each program qubit is going to be mapped, we need to make sure that the reliability of a gate is specified by where it's mapped to. Okay, so first we'll do measurement constraints. Let's see what we were here. We were 6. So for every measurement, so every gate of type, this measurement type, and then for every hardware qubit h, if the qubit that this thing operates on, g.q, for example, equals h, then this is going to imply that the error, we'll use a little epsilon for the error, is equal to some pre-known value e measurement, this big M sub h for that hardware. So this is just this is some like big matrix that's pre-computed and storing the measurement error rates for every hardware qubit h. Okay, and then we should add in some reliability constraints for all the 2-qubit gates. So, for example, for every gate, G again on A and B. For every pair of hardware qubits, H1, H2, if A equals H1, or I guess the hardware location of H1 of A, and the hardware location of B is equal to the second hardware location, then we can just assign the error of that gate to be this pre-computed value EC of H1, H2. So note that this is not necessarily the gate error between hardware locations H1, H2, because H1 and H2 may not be adjacent on the hardware, and so what we want to do is actually look at where did the path that executes a gate between H1 and H2 end up. So back to our example of being distant, and we had to swap there. We actually want to look at, this is going to be the error rate of this edge, but it's also plus all the error along the way. So this term is, this E term here is including all of that error rate, like a large product of those things. Okay, in systems where single qubit error rates are not dominant or are much smaller than 2-qubit error rates, we can usually just omit the 1-qubit gate constraints for error or durations. Okay, so let's finally talk about objectives. So we specified all the things that need to happen, and we can see that's really hard because a lot of these things are integers or include implications. So solving this is going to be hard to do. And we can also choose many different objectives. The first is the same as before. We could just minimize the execution time in which case we don't need to add the reliability constraints, which might make our problem easier to solve. And the second is the maximize reliability, which is a combination of that readout error, 6 and 7, and the gate errors. We could also add in coherence error, but in this case, we'll just assume that the coherence error has been already included in these error terms here. Okay, so then we can write our objective as this epsilon, the sum of all the readouts, just using some shorthand for if these are measurement gates, the log of their error. I should probably use a different term than epsilon here. Let's use alpha, just to avoid confusion. And then we also want to sum over the error, the computation gates. And similarly, log of g dot epsilon. And this will be 1 minus alpha as a term out front, actually. And so the point of these alpha terms is to weight which of these terms we want to consider more important in our objective. And you would need to solve for alpha empirically. Okay, so that was a lot. And what's worse, the solution to this is not efficient. And it also fixed a lot of different things beforehand. We fixed the paths that we needed to communicate, for example. And so we didn't actually give all the possible choices to the solver. And so what solution that we found, the optimal solution to this problem, which we will obtain after a long time, isn't actually going to solve the very generic version of how everything should move around and execute in the device. So it may not actually end up being the best solution for our actual hardware. And so truly finding an optimal solution to this will be hard. To do all these things at the same time is going to be really hard. You could separate out problems and just solve the mapping and then the routing and then the scheduling problem all separately. That'll make it a little bit easier, but it also will lose some of the optimality properties. Okay, to really get optimality, we have to add a lot more variables and which is going to be really hard for anything of even moderate size. And so the heuristic strategies we talked about before end up being really good, and they're also efficient. So developing really good heuristics is usually the focus. Okay. Our optimal solution that we just talked about doesn't even account for all the types of errors even. Let's look at another type of error that we've mentioned before, and that's crosstalk error. Error which is occurring when gates are performed in parallel on device. For superconducting devices, there are several approaches to this problem. First, reduce the device's connectivity. So rather than this grid that we've been talking about, we could instead do something like IBM does, which is to use hexes that are repeating in a repeating pattern, etc. And so this is less densely connected than the graph on the left, than the 2D grid. And so there's a trade-off here because we don't want to be too sparse because then it takes a long time to communicate qubits across the device. We also don't want to be too dense because then maybe our crosstalk errors become dominant. The second approach is to do something called qubit or coupler frequency tuning. So this allows the software to decide which frequency qubits should operate at during execution. Or in the case of coupler frequency, we can dynamically alter the connectivity by possibly just turning off the coupler and assign frequencies in a way that don't interfere. Other common solutions are software solutions. These, I think, are more common. And the idea here is to balance coherence errors due to the increase in duration by maybe saying don't execute two pairs of gates at the same time because we know that they incur a large crosstalk cost. We'd have to know that for the device. So for example, suppose we have this machine on the left where we know that between qubits 0 and 1 and 2 and 3, there's a lot of crosstalk to execute 2 qubit gates in parallel. But we also know that there's low coherence time on qubit 2. And so we need to balance making sure that gates execute quickly on qubit 2, while also not incurring too much cost by executing lots of 0, 1, 2, 3 pairs at the same time. Okay, so we can see here some examples of different schedules for this program, for the program here from B. The first is just to execute things as soon as possible, which would put 0, 1, and 2, 3 gates in parallel, but we know this is high crosstalk, so we want to avoid this. The second says just don't execute any gates at the same time that are 2 qubit gates because we know there could be crosstalk. And so this avoids the crosstalk problem, but now we've forced on qubit 2 a long duration because it has to wait for this gate up here. And so that means there'll be more crosstalk or coherence error on qubit 2. A mixed strategy balances these two things, and here we've inserted a barrier to force this first gate on 0, 1 to occur first, and then the gates on qubit 2. And so we know that this is better for qubit 2 since its active volume starts here and not earlier on. So we've saved all of this extra free duration in the middle. Okay, in this video, we've covered several compilation software strategies that can be used to account for error. Compiling in this way was used to maximize reliability, and it's been shown to be really important and successful, resulting in a higher probability of success for programs in the near term.